Today's lecture will be continuation of this continuous time filters that we had started already, but I will try to finish this content today and at most by Friday so that we can start switch capacitors on Friday itself. We reached to integrator based realization of ladder filters. This is one example like how we make active filters, and then based on that we can make different types of active filters. Means that it's not the only way. As I said, there are different ways and we are not limited. But there are some precautions that we have to take so that to make sure that performance of the filter doesn't change with tolerance in the component values, which happens when we want to have an on-chip filter. And also we want to have proper constraint on the sensitivity of filter to different voltage and temperature variation parameters. So this creates some limitation, like that doesn't give us freedom to choose whatever filter we want. Of course, other issues like, for example, if we want to be low power and other specification, that also will come to the picture. So we will look at this integrator base as a base to learn, and then the remaining part you can learn on your own, but the concept will be similar. Then we will talk about frequency transformation that we didn't have time to talk about it last time, how to convert the low pass to band pass and other types of filters, and then how frequency performance is translated to time domain performance, and then how non-idealities, for example, limited Q variation of components will affect on the performance of the filter. So here I am starting from the point that we were last time. But before talking about this, just a few points I wanted to mention. Okay. So we were here last time. Before starting that, I just wanted to tell you about one reference for filter design. And there are two only books in the library, and the students said like those two books also are taken by two students. So this one thing we can do is I can take a Xerox copy of pages and in the last part and give it to you, or you can check if this is available for you. There is essentially any handbook of filter design will give you parameters. There was a link sent by Naveen. I have not checked the link. You may have checked it. So I don't know, but you need whatever values you get from any tool, specifically if it's a free tool. You double check it by simulator. Make sure the values which are given are correct. So there is this book, Handbook of Filter Synthesis, and Sharma also doesn't give value of L and C. It gives only tables. A.B. Williams. And this is an old book, and there is one more handbook from the title might be this, or it might be Electronic Filter Design. So it's from McGraw-Hill. So values of L and C may be found in this handbook. Essentially, if any sort of handbook you can find, that will give you value of L and C. And you can check the tool Naveen has introduced. Okay, so coming back to the previous lecture, here, if you remember, we created signal flow graph, and then now just I have simplified the signal flow graph here. So if you notice, we had three components, and purposefully I wrote equation in such a way everywhere we will have integrator. Therefore means voltage of capacitor will be a function of its current, and current in the integrator will be a function of voltage. Multiply current by some value, it will convert it to voltage. We call it R star, and then accordingly we will get the signal flow graph. And now we want to convert it, and here if you notice we have two others. We can combine them in one other, therefore it will be simpler, but then the other that we implement using op-amps will have more number of inputs, means that VAI, Vin and VCS. These three will be inputs. So what is the component we use? Two things you can do. First of all, you can imagine you have negative values of resistor or capacitor. Therefore, you can just simply use a single-ended version of this implementation and convert it to differential mode. So, the component we use for differential mode essentially is a differential in, differential out op-amp. In general, we use this type of module. It's a lossy integrator with two inputs. This number of inputs can increase depending on the number of inputs we have in the SFG. Like here we have three. We can have three inputs. So if you notice, everything is differential. This is a differential op-amp. Sometimes it is not shown as a trapezoid. Actually, it is shown as a rectangle with two inputs are taken from two sides. This is usually used for transconductor, but here in general we show it as an active component. And now we will start just implementing a single-ended version and then converting it to differential mode. So for example, if you notice in the simplified SFG, so then you look at the simplified SFG. First of all, if you notice, always you can have just a simple structure for yourself. See, for example, you have VC, V out, it will generate V2, V2 generates I2, and again I2 and I1 generate some component R star IC, and then again it will generate VC. So, for example, this was R star upon SL2, this is adder, this is V out, and this is VC. Then these two will give V2 and this is minus 1. Okay. And this was I2 R star. So then for this, I will make V out, VC. These two are getting added together. Therefore, in the single-ended version, I will have these two coming to the input of integrator. And this will give I2 R star. And this is C. And what is value of C? This is equal to 1 upon SC. Therefore, Cx is equal to L2 upon, and now if you notice, this should be R star. Therefore, Cx is equal to Cx R star is equal to L2 upon R star. Therefore, Cx is equal to L2 upon R star square. So this is Cx. Then now we have this. Now again we come back here. Now these two are just again a simple adder. It comes to the next integrator which generates this. So from here we come back to the right. Again this is stored. one more. This is R2 R star I2 and this is I1, R star I1. And then this goes again to the next C1. So it's here I2 R star R star I1 to other, again another integrator which will generate this. Which is here. So this left and right, when you keep, you will be able to connect this directly to PC. So schematic will be clean. Now again Cy. So Cy is here. Therefore 1 upon SC R star is equal to 1 upon S R star Cy. Therefore Cy is equal to C. So now this is value of Cy. So again we will continue. Now here we have Vc, then we have V3, so these two, and then again it will go to integrator. So here we can put them all together because it's just other, right? Therefore I will have another. So Vc, in fact Vc, this V3 is again is summation of R star I1 and Vin. So Vc one is Vc, one is Vin, and one is R star I1, which is here. Okay, I have not generated that also. Okay, fine. So it will be generated here. This 3. So Vin, Vc, R star I1, this 3 will get added. Now I will correct the signs. Right now I have not considered any specific sign. Then we'll see which one will be negative resistance or positive. R star. And then for this will come with value of R. It's not R star. And Vin also will come with some value of, no, Vin will come, yeah, for this also, call it R1, R2. And CZ, which will generate R star. Both are inputs. So this 3. If we don't put like this, then we will use one simple 2 inputs, and then here we will use a simple amplifier. This means or R star I1 and V are given just to a single inverting amplifier, and the output will be V3 here. And the ratio from R star I1 to this is R star I1 into 1 multiplied by minus Rs upon R star. So overall it will be minus Rs upon Rs. So this is R star I1. This is R star So V in comes by the value of 1. Therefore, this will be R star for V in. And then for R star I1, this should be minus Rs upon R star. Therefore, this ratio R star upon R is equal to Rs upon Rs. Therefore, R is equal to Rs square upon Rs. And then V3 will come to the just two inputs integrator like this. So either this or this. Now we have to correct for this sign. Starting from here, V out was negative, right? Therefore this means this resistor should be negative. Then coming back here, I2 R star, now coming here, I2 R star is negative when it comes here. To generate R star IC and then generate VC. Therefore this should be negative. Then from here, VC is again negative. Therefore we should have a negative sign. So this is VC, so this should be negative. Now, if you notice, all of them have positive value of 1 upon S. But here everything is negative. Therefore all capacitors are negative. So now we just convert this to a differential one. Now if you use differential, then there is no problem of negative components. The reason is when you use differential, you can just change the polarity. For example, I replace the first one. This is minus Cx minus R star. This is V out. Let me double check, make sure direction is correct. For R star I2. For R star I2, it is minus 1 upon SC multiplied by this, it will be positive, then V out negative, VC positive. Correct. Now we want to convert it to a differential one using this module that we have. So either you show it by a trapezoid or a triangle with two outputs coming from sides. So we want to make everything positive. So if you look at the V out, ratio for V out is negative, right? Therefore, suppose I make this R star and this is R star, this is V out plus, this is V out minus, and this is integrator. And now all values are positive. Now what I should do? If this is V out plus and this is V out minus, because the overall sign is negative, therefore here it's enough if I put it like this. So for V out it will be automatically negative. Now what about VC? For VC this is positive. Therefore I have to apply VC negative here and VC positive. So automatically polarity will be taken here. So now we have this component, we replace all these components by this. Similarly, this one, how to convert it to this? Here, see, R star I2 is equal to 1 upon SCX minus 1 upon SCX into V out and plus 1 upon SCX and R star. into VC. Okay. So now if you look, if I take, first you look at V out, okay? So this is V out plus, this is V out minus. Now this is what I get at the output, and this is R star I2 plus, this is R star I2 minus. Now if you look, the gain from this node to this node is minus R star upon SCX. Do you agree? This is positive, this is positive. Right? I am taking this as an output. Now for the case of VC, what I am doing, I am changing polarity of VC at the input. Now what happens? If you look at the differential mode, I will write differential relation. In the case of differential, what will happen? Your input now is VC minus minus VC plus. Therefore, I will have R star I2 plus minus I2 minus, right? This is my output. Minus 1 upon S Cx R star into VC minus minus VC plus. Right? So this will be the equation for VC. And for V out, it will be like this. Therefore, effectively it's like that you have multiplied by minus 1. So here it's very easy by just changing the polarity at the input to control the sign. That's why this differential architecture is very straightforward. And of course it has other yes. See, it's the differential. Therefore, everything is differential. Even at the input, when we want to implement Vin, Vin also should be applied in a differential manner. Yes, at the end it is single-ended. Yes, then we have to convert single-ended differential mode to single-ended at the end. So it has several advantages. First of all, circuit is not sensitive to common mode noise, right? The second advantage is, what is the second advantage of a differential architecture? Any guess? Having more PSRR, right? If you look at it as a common mode noise, yes. See, PSRR also is some sort of common mode noise, right? So therefore it will be less. It will be more in fact, right? So because this is essentially attenuating common mode signals on two rails, right? V in plus and V in minus, V out plus, V out minus. So if a signal comes of the same phase on both of them from a single supply, yes, then it will reduce. So effectively, yes, whatever common mode noise you have, you won't observe it at the output because output is differential. So the only question is whether noise will be same from supply on both rails. See, simple example, it will be consider a simple differential amplifier. In a simple differential amplifier, circuit is symmetric. Therefore, whatever noise you get from VDD on one output, you will get same noise from VDD on the second. Therefore, it's symmetric. Therefore, it will improve PSRR. That is correct. One more thing is because you have two signals of having 180-degree phase shift, you will be able to omit even harmonics. Whatever even harmonics you have will be omitted. Therefore, it will give better linearity. But the only problem is now number of components will be twice. So this is the price with it. So trade-off with performance and error. And of course, if we want to get a single-ended, at the end we have to convert it to a single-ended output. So now, at least now you know, if we have a ladder, how to get an active filter out of it. This is called direct simulation. Why it is called direct simulation? Because I am just transferring that direct, that LC ladder configuration to a active filter configuration. But the question might be, okay, why not, for example, to use a cascade of second order or first order filters, right? This is one of the very common ways of implementing an active filter. So why not to use it? So before answering to that question, so you may have just this, yes. Please repeat your question. You want to say that there will be less number of components here? If you follow that active filter design procedure, you mean cascade? What do you mean from procedure? See, there are different ways, okay? So what we are talking about is a direct simulation. Means that directly you implement, or direct realization. You have an LC ladder. We make a signal flow graph of the ladder. We implement it in the form of a network. Exactly. So it is like mimicking the state equations, right? So it's exactly the signal flow graph. This is one way. The second way is you have an HS. Okay, it's a polynomial in the numerator and denominator. It's a rational function. Now you write it in the form of H1s multiplied by H2s multiplied by and so on. And then now you implement each one of them as a separate filter, cascade them. So it will be multiplication. So what is your question?
We can design with less number of components with single op-amp like. And rest of the RC network is ladder, RC Butterworth. It's like active Butterworth filter design.
Active Butterworth means that just a single op-amp and then use the entire filter around one op-amp.
Yes.
N number of filters, yeah. That is what is called a multi-feedback configuration. That is also, yeah, that is called one of the, today I will talk about that also briefly. So this is another way of implementation. See, the point is, there is some special properties of this ladder which makes it less sensitive to component tolerance if filter has a very good reflection coefficient. Means that if you are able to match input impedance with RS, therefore we will be able, I will explain it. Then now to take advantage of this specific property, people are trying to implement the filters in such a way their signal flow graph will be similar to SFG of a ladder. So multiple feedback is one of them. To create this, because if you notice here, actually it happens. There is multiple feedbacks. Yeah. So then we want to generate multiple feedbacks. So that's what you say is a multiple feedback configuration. That is also one of them. That also has good, less sensitive. You just write down what you did. Yeah, just how to calculate, how you calculate by hand analysis. Just you show the method, that's it, answer it. It's just a simple RC filter, right? So just that high pass filter. That's it. Just how do you calculate and then just write it and draw the circuit, equivalent circuit for noise analysis. Okay. Have you given? Okay. What is a high pass filter? Now we just replace the components, right? So the in is 0 because we are doing noise analysis. R, and there is a noise source associated with R. This is V out. Now what is transfer function? For noise, right? This is V out, this is noise source. You reconfigure it, just I'm redrawing it. Look, for noise it will be a low pass. That is the reason it doesn't show high noise. For noise, it will be a low pass filter. See, noise source is here. Therefore, noise will see a low pass filter. Therefore, noise will be filtered. Exactly like the way it is done, it is achieved in low pass. That was only the small trick in this. And the remaining part, of course, is straightforward, right? Because low pass filter was 1 upon j omega RC plus 1. This was 8j. Therefore, and the remaining part we did. It will be a tan inverse, right? And therefore it will show you the same KT upon C. Yes. Input as white noise. No, that is different. Here we are talking about only circuit noise, not noise which is applied from outside. Inherent noise. Then it will be KT upon C. Okay. Now coming back to this points. Before that, okay, I will talk about this realization, and then I will talk about frequency transformation. So now we know how to simulate SFG. So when we simulate SFG, what happens is we have a transfer function, and this transfer function is a rational function. The coefficients in numerator and denominator are a function of circuit components. Therefore, what happens is, suppose for example, and similarly, for example, AM, J, AM, AM, n minus 1 omega. This is B0, this is B0. When we make a simulation, so suppose you have a component. That component is in L, for example, in some branch, and that L changes or C changes. There is no direct way of translating those variations to these components. What happens is, there is no even unique or one-to-one variation. In the sense that, suppose if you have a component C in the circuit, You cannot say if I have delta C, then I will have delta B J. So this is not correct. What happens is, if you have a delta C, that effect will be translated everywhere. Therefore, all coefficients will change. This is one of the problems with these filters. However, in Schumann's book, there is a theory. It has explained exactly the theory, and it has proved. If we have variations if we design the filter in such a way, rho is equal to 0. What was rho? If I have a ladder filter, a two-port network of half RL, this is RS, and this is LC ladder filter, and this is input. So the impedance I see from here is RS. In that case, I would say that rho, or the reflection coefficient, is equal to 0. In this particular case, and of course RL equal to RS, it can be shown that actually the amount of variation will be very small. And therefore, that is the reason always this filter are being used in a maximum power transfer mode. Means that when reflection coefficient is 0. Because they actually can mimic a very robust filter with respect to variation. And it is one thing which care about it when we talk about on-chip variations and on-chip implementation of active filters. So to be able to compare different architectures with respect to sensitivity to process variations or anything else, even if it is a discrete filter, now we are talking about on-chip variation, a parameter is defined called sensitivity. This is a general definition, but it can be applied to any parameter. Essentially, suppose you have a parameter P as a function of X. Sensitivity of P to X is defined as relative change in P with respect to relative change in X. In other words, it is defined as this. And the being relative is very important because absolute value usually don't make sense to talk about variability. Or other words, it is derivative of P with respect to X multiplied by X upon P. This says that if I have 10% variation in X, what will be the corresponding variation in P? So this is a very important parameter in sensitivity analysis. Important relation in sensitivity analysis. So some of the properties of this sensitivity, for example, will be if you have a function P as a function of Y and Y is a function of X, and then you want to see sensitivity to X, it can be proved like this will be multiplication. Or for example, if you have sensitivity of two functions which are multiplied, so it will be summation of two sensitivities. Or if they are of course divided, it will be minus. No, P is a function of Y, Y is a function of X. No, this is Y as a function of X. Y is a function, yes, it is Y, correct. So it is not always very easy to compare sensitivity of different architectures. But for example, suppose if you have a simple biquad implementation, okay, so now we are talking about two ways until we reach to this multiple feedbacks. So one way will be direct realization, and one way will be cascade of biquad. So which one will have a better sensitivity? It's not very straightforward. There are few things. First of all, in direct realization, if we want to get a good sensitivity, we should make sure that rho as a function of omega is very small, at least in passband. But this is something that we did when we were designing Butterworth or Chebyshev others, because all of them are based on this assumption. What we wanted to do is, we wanted to make rho small, right? If you remember, what was rho? Normalized value of H, right? So in other words, but if you remember in the passband, we were always allowing a limited repel. That limited repel actually defines how this rho will be small. Suppose if we don't have repel and this is an ideal filter, therefore magnitude of H will be always 1, right, in the passband. That means that rho as a function of omega is always 0, right, in the passband. Therefore we will have a minimum sensitivity. In fact, ideally sensitivity will be 0 if rho is 0. That is a very important characteristic of this direct realization. Therefore, in direct realization, rho omega should be kept small in the passband. But what will happen in the transition band? In transition band, there is a rapid increase in rho. Therefore, that transition band will be sensitive now. Therefore, if we are optimizing for minimum sensitivity in the passband, there will be a problem with the transition band. Now, what about the biquad? If we make a cascade of biquads. For example, I just consider two modules, H1S, H2S, and this is V in, this is V out. Now suppose very interesting point is, of course one may say that okay, each one of them again can have a very small rho. That is possible. Means that you can make a cascade in such a way each one of them will have a small rho. Then purpose is served. Another benefit of cascade is, if a parameter changes here, okay, suppose a C changes here, or some R. We are talking about an active RC. If it changes here, it doesn't change here, right? Therefore, transfer function of H1 J omega will be only a function of C or R. But here it won't be a function of C and R. Therefore, if we have a variation here, this won't affect on H2S. This is exactly opposite to the case we have in the case of ladder. In the case of ladder, if we change a component value, it will change many coefficients because all are integrated together. Because if you remember, like for Z in, to realize it was, for example, AS, then 1 upon BS, plus again 1 upon CS, and so on. Right? So if one of them changes, then you see the effect will get translated here, again it will come here, and so on. Therefore, many coefficients will change. But in the cascade, at least you can make them a little isolated. But again, this is not working for on chip implementations, because on chip implementation you cannot say I have a capacitor here which changes with process, and here it doesn't change. Therefore, in cascade of filters, because all parameters are changing, therefore effectively you may see similar problem that is observed in the case of ladder filter if it is not with minimum rho. But one of the reasons it is used a lot in filter implementation is simplicity in the implementation and regularity. Because you can design and optimize what the specific backward as a filter as a library element, and then just put and simply you can scale the values and then make a cascade. So if you want to have, for example, migration to another technology, this is a very straightforward way of doing that by using cascade. So simply, for example, if we have a simple filter, first order, with some gain at low frequency, then and P is equal to some RC, then what should be the sensitivity? So here P is equal to 0 root square 1 plus omega square upon, okay, this is low pass filter. What was your question? Oh yeah. Yeah. P is pole 1 upon RC. So now how this pole will change? Delta P upon P. So for example, with respect to delta C, so it will be 1 upon R, of course, is constant. Derivative of this, which will be C square, and then into delta C upon P, which will be minus delta C upon C. So this is variation of pole. For example, if we make pole as a function of, as a parameter that we want to look, therefore sensitivity of P to C is equal to minus 1. So this means that if we have 20% change in value of capacitor, pole will change by 20%. And usually if we have an LC ladder filter with very small ripple in the pass band, means rho is almost close to 0, it can be shown that this sensitivity actually is less than 1. So sensitivity of any performance parameter to X, absolute value of this will be less than 1 for matched LC filter. And if it is not matched, even it will be much larger than 1. However, if we have a cascade, now it can be shown that. Therefore, I can write in changing the sensitivity. First, matched LC ladder. Second will be cascade of backward. And third will be LC ladder with so this is as per order of sensitivity of HA omega, either magnitude, or phase with respect to x, and x is any component value in the filter. Sensitivity increase. In fact, this is the direction of increase in the sensitivity. So this is for passband. So if you are concerned about passband sensitivity, matched LC ladder is the best implementation, and then simulate. Simulate in the sense that realize it with SFG. However, if you are talking about transition band, both of them have problem. The reason is, specifically in the case of ladder filter, because rho suddenly increases, therefore we will have a jump in the sensitivity. In the case of biquads, usually if biquads have a high Q, again that will be a problem. Because as soon as we reach to the transition band, there is a rapid and very high sensitivity to component value. Because Q is very large, Q of pole. It can be shown that sensitivity, I don't write equations and these things because it's filter theory. But it can be shown that the sensitivity of a transfer function, Hs, is a function of Qi for Z and Qj for poles. If you have n number of zeros, n number of poles. If Q of these poles and zeros are high, sensitivity of Hs to component values, any component value, which eventually means to any pole and zero location, will increase. So if Q increases, this sensitivity will increase. Therefore, designing sharp filters always is a problem. And it is not even if you go with Cascade or if you go with direct implementation. So now, what are other ways we can implement a filter? To get advantage of this small rho for matched LC ladder. So this is something similar to what your friend said. So right now we know two methods. This is a straightforward cascade of biquads. Property of LC ladders is because of multiple feedbacks inherently in the structure of the filter. Therefore, another architectures which are called again direct implementation, similar to direct implementation, are which are very famous. One is multiple feedback, which inherently tries to mimic similar multiple feedback existing in ladders. For example, it has been, so it's some sort of combination of cascading and feedback to take advantage of both. So you have n number of stages and then you give it to the some feedback component, bring it to the input. So this is feedback 1. Then you have similarly feedback 2. So there is a feedback from each output to V and so on. And finally from last. So it's a combination of both. Now we can decide what should be the order of each filter and then how we can control each one of them separately. It's very common to choose the order 2. Therefore, most of these H stages are biquartz. The second architecture, for example, will be like something which is called leapfrog because it is looking like a frog. This leapfrog topology has again this H1. Here is saying H1. Then now, instead of cascading means multiplication, we have addition. Then H2. Again added to HN. Now, each one of them receives a feedback. So, for example, this is input. Each one of them receives a feedback. So, input receives a feedback because this is going to H1. So, it will receive feedback from the next stage, which will be H2. They are all negative. Of course, it depends on the polarity. We assume on positive, so from this side it will be negative. Again, for example, if this is the next stage here, output of this will be given to this. So what is important to generate is multiple feedbacks, but at the same time keep the biquartz in the forward path. So as an example for a multiple feedback, second order, this is an example. MF means multiple feedback. This is single ended. This is AC ground. Everywhere when I draw it's AC ground. So in DC it will be reference voltage. So see, this is the integrator. Now there will be another feedback by this resistor. And this is the R, C1, C2. See, if you compare it with this multiple feedback topologies, for example, you may say that, okay, I have a simple RC, so first one will be just a simple RC and this is input. Now, the second one will be simple integrator. So this simple RC, simple integrator are coming. So see, if this is V out, I will rewrite like this. This is V out. This is V in, right? And these two are coming here. And this is integrator. V out. Now look. This is just like we are adding V out and V in at the input directly. So we had an RC filter, we are giving feedback, adding at the input, and this is integrator. So it is from one aspect, it is similar to this. So it is like that. You have put a low pass filter here. You put an integrator for H1 and then put a feedback, give it back. So this is a simple second order filter. So in this is a second order filter with this transfer function. So is it clear? This is some sort of multiple feedback. So if I write it, I will write here. If I divide by omega 0 square, it will be written in that form. 1, omega 0 will come here, and this will be omega 0 square. Therefore, omega 0 square will be 1 upon r square C1, C2. And Q of the filter, so Q omega 0 will be 1 upon 3 r C2. Therefore, Q will be equal to 1 upon 3 ratio of C1 upon C2. So now you can see a little now how these properties of multiple feedback help. For example, look at Q. Q is dependent on ratio of two capacitors. And usually on cheap implementations, capacitors change in the same manner and in the same direction with each other, specifically if they are not far. And this is a real case. Therefore, Q of filter can be kept almost independent of process variations and can be controlled by ratio of capacitors. And therefore, if you keep ratio of capacitors some constant, therefore here your omega 0 will be controlled by RC, just as one RC. For example, I continue next page. For example, suppose omega 0 is 2 pi 10 to the power 7. We want this, right? And we want Q to be equal to 1. So from here, we get ratio of C1 upon C2 to be equal to 9. And therefore, from here, we will replace omega 0, which was this ratio, 1 upon R to the square C1, C2. Right? Yeah. So then from here, we get value of RC2. So now if I choose for uncheap implementation, so some proper value, suppose if I choose C2 2 picofarad, R will be equal to 2.65 kilo ohm and C1 of course will be 9 times more, which is still is okay, 18 picofarad. And you know, because Q is equal to 1, therefore poles are, what is the property of poles? for q equal to 1. Yes? Please repeat. Yes. So first of all, they are complex, and the second part is this two are equal. Yes. So then now we will have, therefore, in the time domain, the response of this filter will have some sort of ringing performance until it will get damped. And what is the damping time constant? It will, you know this, right? We define, we can write it in some other ways also. I think I don't, I'm not sure if I said this or not, like, see, this was the transfer function, right? So we can write in this way as well, right? It's 2 square plus 2 zeta omega 0 s plus omega 0 2, right? This is same as this. It's 2 plus q omega, plus omega 0 upon q into s plus omega 0 square. Because the reason is because the poles will be as a function of zeta. They write it in this way. But this zeta, in fact, 2 zeta is equal to 1 upon q. What are poles? Is minus zeta p1, p2 plus minus zeta square minus 1. The entire thing will get multiplied by omega 0. So when q is equal to 1, means zeta square is equal to 1 upon 2. No, they are not equal. See, because zeta is equal to 1 upon 2. Therefore, real part will be 1 upon 2 and imaginary part will be root square 3 upon 2. So, and if we have poles like this in the time domain, it will have a component of minus zeta omega 0 t, right, into sine omega 0 t plus some phi. Impulse response. No, that's why I said they are not equal. It will be root square 3. Yeah. No, q anyway will be. No, what q you, so, see, we have two types of q. What q you are talking about? Q of poles or q of filters? Okay. Q of filter is 1, but q of poles is not equal to q of filter. If you look at q of pole, yes, will be zeta into 1 upon zeta square. But q of filter, which is not always equal to q of filter, right? Because q of filter is equal to 1 upon 2 zeta. Here our concern is, of course, these two are related, as you see, but they are not the same, but they are related. Sorry, q of filter is imaginary. It should be 1 minus zeta square upon zeta. So they are related. If you increase q of pole, q of filter will increase, and vice versa. So therefore, now what is its minus zeta omega n0 for us? So this was just a question, that damping time constant. So zeta omega 0 will be equal to, for this particular example, will be 3.2 nanosecond. This is for this particular example when zeta was equal to 1 upon 2. And minus 3 dB frequency will be close to omega 0, but it is greater. That close to omega 0. It's not very far from omega 0. Q was 1. So, the transfer function of this filter will show some peaking. If it is log domain, this should be 0 dB. 0 in the log. So this is dB, and this is omega in log scale. Therefore, it is 0, means omega is equal to 1. So there is a peaking, minus 3 dB frequency will be somewhere here, which is greater than omega 0. And you may know peak value of this will be equal to 1.15. We just need to make this magnitude, derivative of this magnitude with respect to omega equal to 0. Therefore, that will give you omega peak. Omega peak. In fact, normalized value is 1.1. I think it will be 1 upon 2 zeta into, I guess it is. You double check, okay? I think peak value will be 1 upon 2 zeta into 1 upon relative value, 1 upon zeta square. With respect to 0 frequency value. So there is a peaking. You know, sometimes this peaking is too high, means that filter actually has a very high Q, so that it is used as a band pass filter. Because this can be a narrow, can create a narrow band pass filter, and then it can peak to a very high value, and this will be actually 0 dB gain or some small gain, which is not important. Okay, so this was an example of a multiple feedback filter, which is, of course, as your friend said, it's economical because the number of op-amps which are used are less. Okay, and now how parameters will change? Okay, so now here we are able to stabilize Q because it's a ratio. But we are not able to control RC because R and C both will change with the process. And therefore, because of this reason, this characteristic of this filter, where is this slide? Characteristic of this filter, it will be like this. Q will be constant, but then it will shift to left or right due to process variations. And in the process variation, so here omega 0 for this multiple feedback was 1 upon R, 1 upon root square C1, C2. And then because we consider C2 is a constant, K into C1, therefore it will be 1 upon R, C1 and C2 is a constant, so root square K. So what happens is, suppose if R has plus minus 10% variation and C1 also has plus minus 10% variation. If you want to see what is the maximum variation in omega 0, you should consider the case when both of them have minimum value and both of them have their own maximum value. Then that will give you the maximum window for variation. Therefore, delta omega 0 max mean C minus 1 upon R max into C. And that is very important to consider, because in integrated technologies this quite can happen. These two are almost uncorrelated, variation of R and C. So one thing now, till now, we have looked at only low pass filters. But what if, again the same mistake you always make, increasing lecture number. Okay, what if we have a low pass filter and now we want to make a band pass filter, right? For example, this simple multiple feedback or those ladder realizations. So what do we expect from a frequency transformation? Suppose this is omega. I show it by capital omega, normalized value. And this is the real omega I want to get. So when we are talking about a low pass filter, everything was normalized to frequencies between 0 and 1. Therefore, if I want to get a band pass filter, it's enough if I map my band into this band, right? Therefore, effectively, what I want to do is, this is the band I had for low pass filter. And this is the band I have now, omega 1, omega 2, and of course minus omega 1, minus omega 2. So, and we have some center frequency, because I have to consider mapping to 0. So 0 was center frequency. So what we want to do is, we want to map omega 1 to minus 1, omega 0 to 0, and omega 2 to 1. So we have these 3 points. Therefore, we can just use a mapping in the form of omega as a function, small omega as a function of capital omega to do frequency transformation. But one may say that, okay, this is omega domain, we want to use it in S domain. This is okay, because S is equal to J omega, we will just replace omega by S upon J. So how to do it, and then how it will be, how we can have a generalized conversions. So, for example, for the case of high pass, what we want from a frequency till infinite to be translated to a frequency from 0 to 1. So it's vice versa. So here, because if you notice, we have 3 conversions. Therefore, it cannot be just a linear conversion, because we have 3 points in fact. In fact, what we should do, we should make omega as a function of capital omega and then find the coefficients of that equation. That's it. So, here I write the relations. You say which one you may not understand. If I want to convert low pass to high pass, just simple guess. So, I call SY, okay? SY is the new one and SX is the old one. Okay, so this is old frequency, this is new frequency. So if I want to convert low pass to high pass, okay, so this means that starting from this and then going to others. So this is easier, right? This goes to infinite, so I will have only one corner frequency, omega c. 1 minus 1. And here minus omega c infinite. So I want to transfer my infinite on 0, and omega c, for example, will be transferred on 1. See, I want to make infinite to be 0 and 0 to be infinite. Therefore, this says that I should reverse it, right? Therefore, this should be Sx inverse. I need just a normalization factor, right? Therefore, I will convert it to this. So, this is in fact, I should have some normalization factor, okay, coefficient k. So, it will be k upon Sx. What is that coefficient? I want when Sx is equal to omega c, Sy should be equal to 1. This means that k upon omega c equal to 1. In other words, k is equal to omega c. Therefore, Sy is equal to Sx and k is omega c. So, it is omega c upon Sx, or you can write it in this manner, which is more meaningful. You normalize Sx to omega c, reverse it. So, this is very easy to convert low pass to high pass. For example, in this example, multi-feedback filter, in multi-feedback, this was a low pass filter. So, if I want to make it high pass, I need to change S to 1 upon S and of course normalize to omega c, cutoff frequency that I want. But it can be proved, I can show you, it's very easy, that it means simply to change something here. Suppose if I want to change this configuration to a high pass filter, do you guess how I should change components? Yes? C and R, yeah, exactly. So we just need to change C and R. Therefore, you replace C by resistor by C, it will be a high pass version of filter. Now, in the case of band pass, as I said, it cannot be just simple function of just the first order variable. The reason is because I have two values. So, I can ignore omega 0, say what is the proper conversion, omega 1 to minus 1 and omega 2 to 1. And of course, omega 0 says that these two ratios, which difference should be 0. So again, Sy is a function of k. Okay, k is a constant because of this normalization. I will write it in this way. One way that I can write, it will be like if I normalize S to some value, or let us keep it as As plus B upon S. Because, okay, so I will write it in this way. The reason is because if I have a band pass, actually band pass is a combination of low pass and high pass. And if you look at outer frequency, what we want to do is, say omega 0 is on this. If I plot this function, so these are 3 points of this function. It will be something. And for negative frequencies, it will be. Okay, so it's an odd function. It should be. So this is the transformation. So infinite will go on infinite. 0 also will go on infinite. That is the reason I should have S and 1 upon S. Because it's a band pass. Therefore, both 0 and infinite should be transferred to infinite, which is the outer area of this low pass filter. So this small omega is for low pass filter and capital omega is for the filter I would like to have. Therefore, this should be transferred to infinite. Therefore, that is the reason I put S and D. Now, how many variables do we have? Effectively, we have 2. Therefore, we can consider omega 1 and omega 2 and then see what will be the value of omega 0 which will generate 0. So, we consider omega 1 will be transferred on 1, omega 1 will be on minus 1, omega 2 on plus 1, and then what will be now? The omega 0. So, we don't transfer omega 0 to 0, automatically it will be obtained. So, we have these 2, we will replace, we will get value of A and B. In fact, these are the normalized, multiplied by something. And then accordingly, we will get omega 0. Now, what will be omega 0? You do it and then see what will be values. Okay, so then it is like that. We want to have Sy of omega 1. So this is S. Therefore, just we need to replace it by J omega. J omega 1 is equal to J minus J and Sy J omega 2 we want to be plus J. So from these 2 relations you can get A and B, and as you notice this is an odd function which is also the odd function. It's odd means that if you convert omega 1 minus omega 1 you will get J, and omega 2 minus omega 2 you will get minus J. So then in this way it's very easy. Now we can convert the low pass to band pass. Similarly, converting low pass to band reject, and these are in fact the most commonly used. Okay, so any question? We have time. I mean, we can discuss for any doubt you have. At the beginning, we'll see just converting to this signal flow graph to active filter. Is it clear? Everybody understood? Okay, so then what we did, we just had a small discussion about this sensitivity and then practically how we should choose topologies as per what we want. But the moral is transition band is very difficult to control, and it always is one of the things which affects on the performance of the filter with respect to process variation, because group delay also is sensitive in this region. And then how to do frequency transformation, and then what is the corresponding multiple feedback realization similar to ladder, and then we had an example for that. I had actually an example for elliptic filter because it was difficult for most of you, and then there was no such reference. So if you see if that elliptic filter I can solve next time. Okay, just one thing I tell you regarding elliptic filters. You know, elliptic filters have transmission zeros. Okay, because they have transmission zeros, this means that we should have, and these transmission zeros are on the imaginary axis. Therefore, we should have a way of implementing them. So, and it's very easy to understand how we should implement them. Just here. Suppose if you want to have a transmission zero. What is transmission zero? Transmission zero was in the transfer function. Means that if it is the band, then here actually I can reach to 0 in some frequencies. Right? So this is a transmission 0. This is omega. So I will have really an omega z. Therefore I should have a component or combination of component which will give this transmission 0. And it's very easy to implement it in a ladder configuration. In a ladder configuration, components are placed like this. Therefore, if you want to create a 0, it's enough to cut it here, or you cut it here, right? Or you cut it here. Now to cut this, so I call this series impedance, and these are parallel impedances in general. So just enough to cut series impedance. And to cut series impedance means make it infinite. right? Therefore, the best way to make an infinite impedance at some imaginary frequency is to use a parallel DC, which will resonate at that frequency. Therefore, this will be transmission zero, simple. Now the question will be how to convert it to an active one. Because till now we had just a simple integrator. Now this will be a second order one. Okay, but then that is interesting. That the remaining part is straightforward. The remaining part won't change. So you will have other things as usual. But equal to the number of transmission zeros, you will have this LC resonance segments. So I will give an example of elliptic filter. I had it today, but it's too late. So I will give an example of elliptic filter and then implementing these transmission zeros. Okay, one question. Naveen has sent a link. Is it working? Have you checked? Working. So are you able to get values for elliptic filters? Everybody does only for Butterworth. Yeah. Okay. So see if this handbook is available or not, or similar handbook. Yesterday I showed you one handbook from it. See what is found in the library. I'm sure there should be some handbook in the library, IT library. You check, because what we need is just to get value of components. Equi-repel field. Equi-repel means repel in the passband and the stopband, both are equal. So that can be a special case. See, if it is equi-repel, it's an elliptic filter with equal repels. So it's okay. So that is available, that handbook. Is it available in the library? Ebook, okay. Okay, so then that's fine. So now you can design an elliptic filter. Yeah, one thing I tell you, in many cases, this phase distortion is compensated in digital domain by a digital filter after ADC. Therefore, if you are able to implement a sharp filter, it is good, even though you don't have a good group delay. And because of this, if it is possible to compensate it in digital domain, in many cases, that is the reason I'm emphasizing an elliptic filter. Elliptic filter is a very economical filter because it shows the sharpest transition among other classes. And then if you use an elliptic, you will be able to generate a very good transition band with high Q and of course with a less number of components compared to any other. And if Q increases, actually the number of components increase exponentially. So therefore that's why it's a very economical filter if phase distortion can be compensated by DSP. Okay.